After an 800 amp meter bank with 4 200 amp meter disconnects and no main, utilizing 120/240 volts one phase, a suitable wiring configuration involves two 3-inch polyvinyl chloride conduits underground. Inside these conduits, employ two sets of 300 aluminum conductors for each meter disconnect, resulting in a total of 8 sets of 300 aluminum conductors. Considering these specifications, it is unlikely that 90 degrees Celsius lugs will be necessary within the service gear. The 300 aluminum conductors possess an ampacity of 225 amps at 90 degrees Celsius, whereas the 200 amp meter disconnects are rated for 200 amps at 90 degrees Celsius. Consequently, the conductors are appropriately sized for the load, rendering standard 75 degrees Celsius lugs sufficient. Regarding the grounding electrode system, a configuration involving one ground rod, in conjunction with a number 2 tin copper grounding loop encircling the tower and exhibiting a resistance of 5 ohms or less, will provide adequate grounding. This configuration establishes a low resistance pathway for fault currents and guarantees appropriate grounding for the site. A more in-depth exploration into conductor sizing, grounding requirements, and relevant codes is valuable. Let's begin with a more detailed look at conductor sizing. The National Electrical Code, or NEC, provides guidance on conductor ampacity based on insulation temperature rating and termination temperature limitations. Aluminum conductors, like those specified as 300 aluminum, have different ampacity ratings depending on the insulation type, such as THHN, XHHW, or others. The NEC tables, specifically Table 310.15b16, detail allowable ampacities for conductors rated 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. While the conductors themselves might be rated for 90 degrees Celsius, the termination points, such as lugs and circuit breakers, often have limitations of 75 degrees Celsius or even 60 degrees Celsius. Therefore, it is essential to select conductors and terminations that are compatible and to use the appropriate ampacity rating factors as required by the NEC. In this scenario, since the meter disconnects are rated for 200 amps at 90 degrees Celsius, the 300 aluminum conductors with an ampacity of 225 amps at 90 degrees Celsius appear to meet the requirements. However, the 75 degrees Celsius limitation of the lugs may require further consideration. At 75 degrees Celsius, the ampacity of 300 aluminum conductors is lower than at 90 degrees Celsius, but it should still be adequate for a 200 amp load. It is crucial to consult the specific NEC tables for the exact ampacity rating at the relevant temperature. Next, we turn to the topic of conduit sizing. The use of two 3-inch polyvinyl chloride conduits underground appears reasonable for housing the conductors. The NEC dictates the maximum number of conductors allowed in a conduit based on the conduit size, conductor size, and conductor insulation type. Chapter 9 of the NEC provides tables that specify the allowable fill percentages for different conduit types. It is essential to calculate the cross-sectional area of all conductors in each conduit and ensure that the total area does not exceed the permitted fill percentage. Using two conduits distributes the conductors, reducing the fill percentage in each conduit and simplifying the pulling process. This configuration also provides redundancy, enhancing the reliability of the electrical system. The selection of polyvinyl chloride conduit for underground use is a common practice given its resistance to corrosion and ease of installation. However, it is important to bury the conduit at the correct depth, as specified by the NEC, to protect it from physical damage. Furthermore, the use of appropriate fittings and couplings ensures a watertight and secure installation. The grounding electrode system is a critical aspect of electrical safety, designed to provide a low impedance path for fault currents, thereby facilitating the operation of overcurrent protective devices like circuit breakers and fuses. The NEC specifies the requirements for grounding electrode systems in Article 250. The use of one ground rod and a number 2 tinned copper grounding loop around the tower with a resistance of 5 ohms or less seems to comply with the basic grounding requirements. The ground rod provides a connection to earth, while the grounding loop encircling the tower enhances the effectiveness of the grounding system. The 5 ohms or less resistance requirement indicates that the grounding system is designed to provide a very low impedance path to ground. This low impedance is essential for rapidly clearing ground faults and minimizing the risk of electric shock. The number 2 tinned copper conductor is a common choice for grounding loops due to its corrosion resistance and adequate ampacity. Tinned copper is especially well suited for direct burial applications as it resists corrosion in soil. The NEC specifies the minimum size of grounding electrode conductors based on the size of the service entrance conductors. In this case, a number 2 tinned copper conductor is likely adequate, but it is essential to verify this by referring to the appropriate NEC tables. In addition to the ground rod and grounding loop, other grounding electrodes may be present at the cell tower site, such as metal underground water pipes or metal building frames. Connecting all available grounding electrodes together to form a comprehensive grounding system is often advantageous. The NEC emphasizes the importance of bonding all metallic components that could become energized, such as conduit, equipment enclosures, and cable trays. Bonding ensures that all metallic parts are at the same electrical potential, minimizing the risk of shock. Bonding jumpers are used to connect these metallic components together, creating a continuous ground path. Proper grounding and bonding are crucial for electrical safety and compliance with the NEC. Periodic inspection and testing of the grounding system are essential to ensure its continued effectiveness. Soil conditions can change over time, affecting the resistance of the grounding electrodes. Regular testing helps identify any degradation in the grounding system and allows for timely corrective actions. The equipment grounding conductor, or EC, plays a crucial role in providing a low impedance path for fault currents back to the source. The EGC is typically a wire that runs along with the circuit conductors and connects to the equipment enclosures and other metallic parts. The EGC must be properly sized according to the NEC and securely connected to all equipment. In a properly grounded system, a ground fault will cause a large current to flow through the EGC, tripping the circuit breaker or fuse and energizing the circuit. Without a properly sized and installed EGC, ground faults can persist, creating a shock hazard. Surge protection is another important consideration for cell tower sites, which are often located in exposed areas and susceptible to lightning strikes and other voltage surges. Surge protective devices, or SPDs, are designed to divert surge currents away from sensitive electronic equipment, protecting them from damage. SPD are typically installed at the service entrance and at other strategic locations throughout the electrical system. The selection of appropriate SPD depends on the voltage level, surge current capacity, and the type of equipment being protected. The NEC provides guidance on the selection and installation of SPD in Article 280. Regular inspection and testing of SPD are essential to ensure their continued effectiveness. SPD have a limited lifespan and may need to be replaced periodically. Coordination studies are an important part of designing a safe and reliable electrical system. A coordination study analyzes the overcurrent protective devices in the system, such as circuit breakers and fuses, to ensure that they are properly coordinated. The goal of coordination is to ensure that the device closest to the fault opens first, minimizing the extent of the outage. A well-coordinated system improves system reliability and reduces the risk of equipment damage. Coordination studies typically involve calculating the short-circuit currents at various points in the system and comparing the time current characteristics of the overcurrent protective devices. The results of the coordination study are used to select the appropriate settings for the circuit breakers and fuses. Short-circuit studies are another important aspect of electrical system design. A short-circuit study calculates the magnitude of the short-circuit currents that can flow in the system under fault conditions. This information is used to select equipment with adequate interrupting ratings. The interrupting rating of a circuit breaker or fuse is the maximum short-circuit current that it can safely interrupt. If the short-circuit current exceeds the interrupting rating of the device may fail, potentially causing significant damage. Short-circuit studies typically involve modeling the electrical system and using computer software to simulate fault conditions. The results of the short circuit study are used to select equipment with adequate interrupting ratings and to ensure that the system is properly protected. Arc flash studies are also crucial for electrical safety. An arc flash is a dangerous electrical explosion that can occur when a short circuit occurs in the air. Arc flashes can generate tremendous heat and pressure, causing severe burns and other injuries. An arc flash study calculates the potential arc flash hazard at various points in the electrical system. This information is used to determine the appropriate personal protective equipment, or PPE, that workers must wear when working on or near energized equipment. The arc flash study also helps identify ways to reduce the arc flash hazard, such as by using current limiting devices or by changing the system configuration. The NEC requires that arc flash hazard assessments be performed and that appropriate PPE be used. Electrical safety training is essential for all workers who work on or near electrical equipment. Training should cover topics such as electrical hazards, safe work practices, and the use of PPE. Workers should be trained to recognize and avoid electrical hazards and to follow safe work practices at all times. Training should be provided regularly and should be tailored to the specific tasks that workers perform. The NEC requires that electrical workers be qualified for the work they perform. Qualified persons are those who have the skills and knowledge related to the construction and operation of electrical equipment and installations and have received safety training to recognize and avoid the hazards involved. The electrical drawings for the cell tower site should include detailed information about the wiring, grounding, and overcurrent protection. The drawings should show the location of all electrical equipment, the size and type of conductors, the conduit sizes, the grounding electrode system, and the overcurrent protective devices. The drawings should be reviewed and approved by a qualified electrical engineer. The electrical specification should provide detailed requirements for the materials and workmanship used in the electrical installation. The specification should reference relevant industry standards, such as the NEC, and should specify the quality and performance of the electrical equipment. The specification should be reviewed and approved by a qualified electrical engineer. The electrical inspection is a critical step in ensuring the safety and compliance of the electrical installation. A qualified electrical inspector will examine the installation to verify that it meets the requirements of the NEC and other applicable codes and standards. The inspector will check the wiring, grounding, overcurrent protection, and other aspects of the installation. Any deficiencies identified by the inspector must be corrected before the installation is approved. The electrical permit is a legal document that authorizes the electrical work to be performed. A permit must be obtained before starting any electrical work. The permit application typically requires the submission of electrical drawings and specifications. The permit is issued by the local electrical authority and is subject to inspection. Record keeping is essential for maintaining a safe and reliable electrical system. Records should be kept of all electrical work performed, including inspections, tests, and repairs. These records should be readily available for review by authorized personnel. Regular maintenance is essential for ensuring the continued safety and reliability of the electrical system. Maintenance should include periodic inspection, testing, and cleaning of electrical equipment. Any deficiencies identified during maintenance should be promptly corrected. Load calculations are essential for determining the appropriate size of the electrical service and the feeders. The load calculation should take into account all of the electrical loads that will be connected to the system, including lighting, equipment, and appliances. The load calculation should be performed in accordance with the NEC. Demand factors are used in load calculations to account for the fact that not all loads will be operating at the same time. Demand factors are typically less than 1.0 and are based on the type of load and the expected usage pattern. The NEC provides demand factors for various types of loads. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC provides guidance on the maximum allowable voltage drop. Power quality is a measure of the quality of the voltage and current waveforms in an electrical system. Poor power quality can cause equipment to malfunction and can reduce the efficiency of the electrical system. Power quality problems can be caused by harmonics, voltage sags, voltage swells, and other disturbances. Power factor is a measure of how effectively electrical power is being used. A low power factor can increase the current flowing in the system, which can increase losses and reduce the capacity of the system. Power factor correction can be used to improve the power factor and reduce losses. Harmonics are distortions in the voltage and current waveforms that can be caused by nonlinear loads such as electronic equipment. Harmonics can cause equipment to overheat and can interfere with the operation of other equipment. Harmonic filters can be used to reduce harmonics. Transient voltage surge suppressors, or TVSS, are devices that are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning, switching operations, and other disturbances. TVSS devices divert the surge current away from the protected equipment. Uninterruptible power supplies, or UPS, are devices that provide backup power in the event of a power outage. UPS devices are typically used to protect critical equipment, such as computers and servers. Generators are used to provide backup power in the event of a power outage. Generators can be sized to provide power to the entire facility or to only critical loads. Automatic transfer switches, or ATS, are used to automatically switch between the normal power source and the backup power source. ATS devices are typically used with generators and UPS devices. Remote monitoring systems can be used to monitor the performance of the electrical system. These systems can provide real-time information about voltage, current, power, and other parameters. Remote monitoring systems can also be used to detect an alarm on abnormal conditions. Preventative maintenance programs can help to ensure the continued safety and reliability of the electrical system. These programs should include regular inspections, testing, and cleaning of electrical equipment. Infrared thermography can be used to detect hot spots in electrical equipment. Hot spots can be caused by loose connections, overloaded circuits, or other problems. Ultrasonic testing can be used to detect electrical arcing and corona. Arcing and corona can be caused by insulation breakdown, loose connections, or other problems. Cable testing can be used to assess the condition of electrical cables. Cable testing can detect insulation breakdown, conductor corrosion, and other problems. Ground resistance testing can be used to measure the resistance of the grounding system. A low resistance is essential for ensuring the effectiveness of the grounding system. Insulation resistance testing can be used to measure the resistance of the insulation in electrical equipment. A high resistance is essential for preventing electrical shocks.